we're going to do a little activity where we're going to hang some mass from a string, and we're going to predict the forces in those strings, or at least in one of the strings, using the procedure that we've been talking about. So first, though, let's the first part, let's do an introduction. And I want to work a problem with you. Suppose I've got a big chunk of mass like this, and it's on a hook. And this chunk of mass is 2 kilograms. And what I'm going to do is I'm going to tie a string to this, and I'm going to pull to the left with a force. I'm going to call this F1. And I'm going to say F1 is equal to 30 newtons. Now I want to keep this thing in equilibrium. So I think you can see that gravity's pulling this thing down. Somebody's pulling this thing to the left. So somebody has to pull up and to the right to keep this thing hanging there. Doesn't that make intuitive sense? So there has to be some F2, some other applied force, to pull on this to keep this hanging mass in equilibrium. So let's say that this is what's given. And here's what we're trying to find. I want to find F2. That is, I want its magnitude in newtons, and I want its angle in degrees, its magnitude and direction. Does that make sense to everybody? Because I don't know what angle this is, and I don't know how strongly I have to pull. That's what I have to figure out. So let's solve this. Well, I'm going to use the procedure. I'm going to draw a free body diagram of where all these forces come together, right there. So here's the free body diagram right there. And of course I've got gravity pulling straight down. Now this is 2 kilograms. So this is mg. And mass times gravity, the mass is 2 kilograms, and what is g? 9.8 newtons per kilogram. So what is 2 times 9.8? 19.6 newtons, at least in the northern hemisphere. All right. Now, I know that this is given to be 30 newtons. And here's F2. Well, let's establish, now this is step 2, right? Drawing a free body diagram. It shows all the forces acting in the problem on the object of interest, which is this little dot right here. I mean, you can consider this little dot the mass. And so I need to establish an axis system, step 3. Let's make this X and this Y, kind of a standard thing. There's no reason to tilt the axis system in this problem because the 2 out of the 3 is already lined up vertically and horizontally. So I'm just going to leave the axis system the way we usually have it. And then I have to take F2 and break it up into its X and Y components. So here's F2X. That is, this is F2 in the X direction. So what am I going to call this one? F2 in the Y direction. And I'm done with step 3. Okay. Look, did given, find, and solve with a picture? Step 1. Drew the free body diagram. Step 2. establish an axis system and broke up any forces into their x and y components. That's step 3. Now on to step 4, which is to sum the forces in the x direction equals ma in the x. We're using Newton's second law in the x and y direction now. And if I look at this problem, I can say, okay, look, F2 in the x is pulling to the right, but I've got 30 newtons pulling to the left, so this is going to be minus 30 newtons. Now, what is the acceleration of this mass if it's just hanging there? 0. It's not accelerating at all, so this will be 0. So this tells me the F2 in the x must be equal to 30 newtons. So in other words, when you pull up into the right, you have to basically pull to the right with 30 newtons to keep this thing in equilibrium. Yes?
Yes.
Okay. Now let's sum the forces in the y direction equals ma in the y direction. If I look in the y direction, I've got F2 in the y, and then minus 19.6 newtons, that's the weight pulling down. And those are the only two forces in the y direction. And there is no acceleration in the y direction, so these are going to be equal to 0. So now I've got F2 in the y is equal to 19.6 newtons. And now it's just using a little arithmetic to figure out what we want. What do we want? We want to know the magnitude of F2 and the angle of F2, but now I have the x and y components of F2. So what do?
Convert.
Yeah, I just convert it from rectangular to polar coordinates. So F2, the magnitude, is going to be equal to the x component squared plus the y component squared. Now, I don't have a calculator up here, so I'm going to ask you guys to do that. Who's good with a calculator? Who's got a fast hand? Jackson? Okay. Jackson is on it. Now, let's figure out what the angle is. The inverse tangent of the y component divided by the x component, just like we've done before. Do I have to add 180 degrees to this answer? No. When do I add 180 degrees? When the x component is negative. But look, F2 in the x is positive. It's in the right, and it's in the first quadrant, so we don't need to mess with that. And so somebody who's got a fast hand for figure out the angle here. Jackson, you want to do that too? Okay. So, well, why not is not part of this problem, but okay. So what did you get it for F2? 35.8 newtons. And what did you get? Anybody get the angle yet? 33. Yeah, 33.16. How about we'll call it 33.2, round it off, degrees. Now let's just restate my answer here. F2 is equal to 35.8 newtons at an angle of 33.2 degrees. Now really what we've done here is we've made a prediction. We've said if I hang a 2 kilogram mass off a string and I pull it to the right with 30 newtons, to keep that in equilibrium, I need to pull up and to the up and to the right with 35.8 newtons of force at an angle of 33.2 degrees. Now, by the way, this is a knot right here. This is not a continuous string. Okay, so because if it was a continuous string and there was no friction, this wouldn't work. But if we're going to actually hang this mass with a string, where these two forces can be totally independent of each other. Okay, so here's what you're going to do now. We're going to do part 1 of the lab right now before you go. So let's do part 1. Part 1's all about the theory. Well, Newton's laws are only a theory. Only a theory. It's a mountain of evidence to support it, and you're gonna gather some here today. So, what we're gonna do is set up the same problem. You're gonna have a string tied to a hooked mass. But now the mass is going to be equal to 1 kilogram. And you're going to pull it to the left, but F1 is going to be equal to blank newtons. I'm going to give you the number of newtons depending on what group you're in. And every group's going to have a different value to put here. So hold on, I'm going to give you that value in just a minute. And then F2 is going to be tied to here separately. You're going to pull on a string, and we're going to use spring scales to measure these. So this is what's given. And here's what I want you to find. I want you to find F2, blank newtons, blank degrees. I want the magnitude and direction of F2. So you're going to basically do what we just did, but you're going to do it for a different mass and a different F1. Now, I'm going to give you the values for it. I need to cover this up. So let me put this in here and magnify it. Now F1, I put the magnitude and direction here. What's the direction of F1? It's 180 degrees, right? To the left is 180 degrees. You don't really need to worry about that. But here's the magnitude of F1. If you are in group 1, it's going to be 8 newtons. So those of you in group 1, put in 8 newtons and start working the problem. If you're in group 2, it's 9 newtons. If you're in group 3, it's 10 newtons. Group 4, 11 newtons. Do you see the pattern here? Group 5, 12 newtons. Group 6, F1 is 13 newtons. Group 7, it's 14. And group 8 is 15. And group 9 is 16 newtons. So what we're going to do is, as we go around in the classroom, each group is going to pull with a slightly higher force, and we're going to see how that affects the magnitude and direction of F2. And we're going to compare each other's results.
You look at 1 kilogram, right?
Yeah, 1 kilogram mass. Everybody's going to have the same mass. Use 1 kilogram of mass. Okay. So let's do that. Solve. So solve your problem. Whoops. Let me zoom back out. So go ahead and solve your problem now, and that'll be good enough for today. Friday, we will actually do the lab, and we'll compare what you calculated and what you measured. And you know what? It'll be right on. So that's a good thing. Okay, that's it for today.